first webinar in a series to take place here in 2026. I am Heather Torlina. I am the Water Quality Associate for Williams, Fulton, and Lucas County here in Ohio, and I will be your moderator for today. Today's webinar is going to feature three speakers who I'll introduce shortly, who are going to provide a Lake Erie HABs, Harmful Algal Bloom, summary for last year, 2025. If you aren't familiar with the water quality team, here's a look at who they are and what territories they cover. Feel free to reach out to any one of us with questions that you have. We also have a website you can check out at waterqualityextension.osu.edu. So, as for today's webinar, we have three speakers. So, just a little bit of background on each speaker. First up will be Sara Guiher, who is the Harmful Algal Bloom and Water Quality Specialist for Ohio Sea Grant Extension. Her outreach programs are focused on connecting people with up-to-date HAB research to increase environmental awareness and stewardship. So today, Sara is going to give a summary of the 2025 bloom season and provide updates on efforts to better understand HABs in Lake Erie. Next up will be, I know we're going to go a little out of order. We're going to go Dr. Justin Chaffin, who is the research coordinator at Ohio State University's Stone Lab, located on South Bass and Gibraltar Islands in Lake Erie. His research focuses on the effect of nutrients, temperature, and light on cyanobacterial bloom growth and toxicity. And Dr. Hans Paerl is a professor of marine and environmental sciences at the University of North Carolina, Chapel Hill's Institute of Marine Sciences. His research addresses microbial mediated nutrient carbon cycling and primary production dynamics, environmental controls, and management of harmful algal blooms, and assessing the effects of human and climatic alterations of water quality and sustainability in both inland and coastal marine waters. So for today, Dr. Chaffin will give examples of a specific well, Dr. Paerl will be giving examples from around the world to show the role of nitrogen in bloom development and toxicity. And then before that, Dr. Chaffin will give examples specific to Lake Erie. All right, so CCA credits will be offered for this webinar, and that will be made available to you at the end of this presentation, so stay tuned for that. If you have any questions throughout the webinar for our speakers, please feel free to write them in the Q&A or the chat feature, and we will ask them at the end of today's webinar. So without further ado, Sara, I believe you are up first. I will go ahead and stop sharing, and you may share your screen at any time.
All right. Okay. Well, hello, everyone. Thank you for joining. My name is Sara Guiher. Like Heather said, thank you for the introduction. And I will just get right into my presentation. So first, I just wanted to say thank you first to my co-presenters. Excited to hear more about what they're doing. I do hear about it regularly, but it's always nice to get a more comprehensive update. Our director for Ohio Sea Grant, Chris Winslow, we work together closely. So if you see some things in my presentation that are familiar, it's because we do try to have a pretty consistent message. We just talked this Monday actually about this presentation. So thanks for the support there. And then I do share information from NOAA. And then I also want to thank the Great Lakes Center for Freshwaters and Human Health, who I've been working with since I started with Ohio Sea Grant in 2024. Okay, so something that I neglected in several presentations until someone said, hey, we could maybe use a little background on what harmful algal blooms are. So to make sure that we're all starting in the same place, just want to give some basics. Harmful algal blooms are caused by algae and cyanobacteria. You might see CHABs. So the Great Lakes Center, we do refer to them as cyanobacterial harmful algal blooms. They're both marine and freshwater. They occur around the world, which Hans will tell you about. They are important. So, in food webs and in oxygen production, um, but they become harmful. We classify them as harmful because of multiple reasons. So it can be because of their toxins. Good news is that there's a small proportion that are actually toxic, and there's a range of potency in the toxin. So some can be more harmful than others. An example of physical changes to habitat could be if thick mats form on the water, and then also if you are familiar with changes to drinking water practices, you'll know that there are high costs and a lot of adjusting that needs to happen for treatment, and then you also have to consider the costs of any health impacts. And again, this is around the world. Okay, and then Lake Erie. I like to say it's small but great. So I one of my favorite parts of my job is talking up Lake Erie and hopefully getting people to understand it a little bit more. So I know that Justin and Hans will both talk about um, kind of the mechanisms and the dynamics of blooms, but Lake Erie being shallow, warm, and productive does make it more prone to things like harmful algal blooms, although they do occur in all of the Great Lakes now. It's very important. Lake Erie gets a lot of attention because of its drinking water source for so many people. It's also bordered by 4 U.S. states and Canada, so I work regularly with partners in the other states and Canada. And there's also those economic considerations. So coastal tourism is valued at about 20 billion now. And there are many things that people enjoy on Lake Erie, including fishing, different types of recreation. I kayak regularly on Lake Erie, beaches, and more. Okay, so looking over the years at harmful algal blooms in Lake Erie, this is satellite imagery um, looking from 2002 up in the upper left-hand corner to 2025 in the bottom right. So you can see that we have variation over the years. I think you can see in the middle here where we had some really attention grabbing years. 2014 when we had the water crisis wasn't necessarily as impressive of a bloom, but it was just the perfect set of circumstances that set up the bloom to be near the water intake. Um, and then we do have, looking at 2025, um, it looks from the satellite imagery to be one of the more mild years. And that does bear out in this graphic, looking at sorry, with one screen, I have to keep, hold on. Okay, I got rid of one thing. Okay, perfect. Looking at the severity index produced by NOAA. So looking at the top there, you'll see that none would be 0 to 1, up through very severe over 7. And you can kind of see a hopefully a positive movement here towards that mild to moderate bloom since about 2020. So we've been following that and looking at those years and wanted to see whether that was bearing out in the data. So this is for the Maumee River. This is flow normalized load. So if you haven't heard of that, that's basically accounting for years that are really wet and really dry. So that can make this data kind of bounce up and down. So this is based on how much you're getting with the flow. And we do have, I don't know if people can unmute or comment, but so we see two lines here. We have all years where we're seeing about a 10% decrease in that dissolved reactive phosphorus. So that's what's really available to things like cyanobacteria. And then with water year 19 excluded, so 2019 excluded, it's about 6%. 2019, we had really, really high rain. Those of you who are producers that are on the webinar, I'm sure that you remember that, which left a lot of acres not planted, not fertilized. So taking that out gets rid of that anomaly. Okay. And then moving into a couple of different um, projects that are going on. So I did mention the Great Lakes Center for Freshwaters and Human Health. You'll see in the picture on the left, that is Hans and Justin are both in there, if you can find them, depending on the size of your screen. And so this is project one, looking at, there's four main projects as part of the center, each with multiple um, leads on these research projects. So you'll see at the bottom all of these logos. It is a large partnership of different institutions that are working to learn more about harmful algal bloom. So first project is looking at environmental variability, so like really large storm events, droughts, cold snaps, high temps. How can and nutrients affect harmful algal blooms? Project two is looking at how toxins are distributed in a bloom. So um, what organisms are in throughout a bloom and what toxins they're producing, and then what their effects are either alone or combined. So it's important to know, those individual toxins, how they might affect you, but then also if they're combined, do they have a different effect? Project three focuses on the environmental variability again, and how it might affect atmospheric transport of toxins. So if those toxins are airborne, first of all, how are they becoming airborne, depending on these different environmental conditions? And then how are they moving around? And then project four is focused on the impacts of harmful algal blooms on human health. Okay, and I did want to plug, so Ohio Sea Grant is taking the lead on or for the community engagement core, and this is another part of the Great Lakes Center. And we're really looking to take all of this work being done and all of this information being gained and connect it with different communities, different stakeholders, people who need to hear about it. So a lot of my job is just going around and talking to anyone who will let me talk to them. So anyone from grade school students through college, and then beyond elected officials, farmers. So yeah, we want to meet, reach as many people as possible. Um, some projects that are included as part of the community engagement core is connecting charter captains with monitoring during bloom season. So um, Ohio Sea Grant is actually a part of that. Winter surveys with the U.S. Coast Guard is another thing. So the ice breaking vessel there on the left, I think that's always a fun picture to share. So when they're out on the ice covered lakes, we can have people collecting data during the winter. We also want to recruit and train the next generation. So that's where the work with students comes in. And then definitely communicating that human health aspect of the research. Okay. And then moving into the agricultural side of things, this is work that is being done, and that was done by Dr. Miriam Carr at Ohio State. And so their work looked at different practices and how effective they were at removing or reducing dissolved reactive phosphorus from a field. And these are the top four practices. So you'll see subsurface placement and manure incorporation both had 48% and 41% reduction when used at the field. And then rate reduction of fertilizer and wetlands were lower, but they were still in those top four most effective practices. And so taking that up to the watershed scale, modeling that, if you double the implementation. So from uh, the numbers before 2018 to 2019, that is predicted to reduce dissolved reactive phosphorus by 20%. So I mentioned before, we're seeing like a 6 to 10% reduction is the best estimate right now. And then we could see a greater reduction through that, hoping to get to that 40% reduction. And then total phosphorus down by 10%. So these are really effective for that dissolved reactive that we're most concerned with. So that makes us think of management actions and how we can have greater impact. So we would love to see an emphasis shift to those practices that are more effective. So, um, if it's a funding program, if it's an education program, if it's um, a program that is um, provided to farmers in any way, we would love to see emphasis on that subsurface placement and the manure incorporation. So those seem to be really promising ways to keep moving the needle forward. And then looking at some work from 2025 from Byers et al., and that is led out of USDA. Um, they looked at legacy or old P. So you've probably heard it one of those ways. Um, and they looked at high um, P fields, so high soil test phosphorus. So that is anything over 75 for your soil test phosphorus in that high or very high range. Those will disproportionately contribute to the loss of dissolved reactive phosphorus at the field. So if um, if the old P fields would be 5% of fields, so this work was data from 41 fields and then taking that out to a larger scale. If in the scenario where 5% of fields in a watershed are of those high or very high measures, then they will contribute 17% of the loss. So not proportional to their presence in the watershed. And then if there are 10% of fields, then we're looking at a 34% loss. And so again, looking at things that we would like to see happening moving forward, some ways to address that, those fields, if there's old P or a lot of dissolved reactive phosphorus coming off of them, um, we can do water management, but really focused on those, on what works well for those high test fields. So in the bottom left here, we have an example of wetlands that are designed to intercept water coming down a river. So this is not, right at the edge of a field, but this is a way that water could be intercepted as it's coming off of a field. So if you're thinking of a ditch, you could have it routed into wetlands, which will hopefully take up some of those nutrients. You can go more engineered and do something like a phosphorus removal structure or a phosphorus trap at the edge of field. Or we really like these modified blind inlets that are coming out. So modified in the way that they have materials that are more effective at holding on to phosphorus. And that is all I have so that Justin and Hans can go into more detail.
All right. Can everyone see my screen?
Looks good.
All right, great. So I'm going to talk about Lake Erie algal blooms and highlight the role of phosphorus and nitrogen. We all know that phosphorus is a critical component, but nitrogen is equally important. Um, so we know for decades that phosphorus is important. Um, Work by David Schindler and others. For example, this experiment where there's this lake in Canada where they divided it. It's shaped like figure eight, so they easily divided. To the top half of the lake, they added carbon, nitrogen, and phosphorus, and a bloom developed. To the bottom half of the lake, they added carbon and nitrogen, no phosphorus, and no bloom developed. Back then, the argument was, is carbon causing these blooms, and it's not phosphorus. But this study and many others pinpointed, phosphorus as being a key contributor to high levels of algae. And what I'm going to talk about is that the role of nitrogen in these. So in both these scenarios in this lake, nitrogen was added, and we believe that phosphorus with nitrogen makes the blooms a lot worse than just phosphorus alone. So we need to look at phosphorus and nitrogen. Um, Sarah already gave somewhat of an introduction. There's hundreds of thousands of different types of algae in lakes. They come in all different sizes, shapes, and colors. But the ones we're focused on in Lake Erie are the cyanobacteria, also called blue-green algae. In Lake Erie, there's three main ones. Predominantly, the ones that when we talk about Lake Erie blooms, we're dealing with microcystis. Okay, microcystis is the main player in Western Basin blooms. It's this one here. This is the one that produces the microcystins, the toxin that we're concerned about. We also have a few other types of blooms. We have planktothrix in bays and rivers and nearshore zones. Many inland lakes have planktothrix. And then we also have Dolichospermum, um, late summer in the Western Basin, but we also have it in the Central Basin. So Lake Erie blooms are visible from satellite, and Sarah already showed you um, this this satellite image, and you see the year-to-year differences. And she showed you the bar graphs that show, big blooms followed by small blooms and vice versa. And she talked a lot about phosphorus. So what is driving this? There's a good correlation between springtime phosphorus load, what you have plotted here, and bloom levels. So in years when we get more phosphorus loaded, we get a lot more algae. Years when we get less phosphorus, we get low algae. So this is an easy interpretation to show. Not all lakes work this cleanly. And this is primarily driven by rain. When we get a lot of rain in the spring, we get a lot of phosphorus and nitrogen runoff, and we get larger blooms. You might have also heard a 40% phosphorus load reduction target. So obviously, we want to be on the left side of this graph where we're getting less phosphorus and getting a smaller bloom. Looking at phosphorus concentrations over time, Sarah somewhat showed this, but this data is going back to 1974. And we see this kind of U-shaped pattern. We have blooms in the 70s and 80s. We have blooms in the 2000s. And when phosphorus levels were low in the Maumee River, we had no blooms. However, the difference between blooms in the 70s and the blooms now, they're completely different genera. The blooms back in the mid 90s the mid 1900s were Dolichospermum, which they can tolerate low levels of nitrogen. The blooms we have now are microcystis, and microcystis requires a lot of nitrogen. So what led to this drop in phosphorus in the 70s and 80s? Well, this was improvements in sewage treatment, removing phosphorus from detergents, and farmers using less fertilizer. The increase in phosphorus, and no, this is dissolved phosphorus. So the increase here is not more phosphorus, but it's how it has been applied. Broadcast applications and tile drainage led to this increase. More recently, Sarah pointed this out, but we do see a downward trend, and hopefully this is signals of success pointing to best management practices and the H2 Ohio program. Some problems associated blooms. One of the main ones for human health and pet health, environmental health, is they produce toxic secondary metabolites. We call these cyanotoxins. The main one that I'm going to talk about in Lake Erie is microcystins. However, we're learning that microcystis produces a whole bunch of compounds that have toxic effects on wildlife and people. But microcystins are the most commonly measured, and the one that everyone has been focusing on. There can be taste and odor problems associated. If you're just walking by a beach, you can get a sulfur smell. Large economic impacts. associated with drops in property value, water treatment, and loss in tourism. Um, for the microcystins, looking at the health effects, they can target the liver, and those with already impaired livers, non-normal livers, such as non-fatty alcoholic liver disease, are more susceptible to microcystins. And then the toxins, the microcystins can become aerosolized. And if you have asthma or COPD or other respiratory issues, microcystins can further exacerbate those conditions. So we're worried about microcystins, and we want to know, is there a simple relationship between bloom biomass and microcystin concentration? So can you look at a green body of water and assume it's toxic, okay? Or vice versa, if the water looks clear, can you assume there's no microcystins? So this is data that Stone Lab has collected over the past decade or so in Lake Erie. Um, we have cyanobacteria biomass on the x-axis and microcystins on the y, and you can see that there's really no relationship between the two. We can see that when there's very little cyanobacteria, we're not getting high levels of microcystins. But let's zoom into where most of the data lies, remove some of those outliers, and then you can really see that microcystin concentrations cannot be predicted from biomass alone. There's over 2,000 data points on this slide, and then you can see that the variability, if you have super green water, you can have high concentrations of microcystins or you can have zero microcystins. And the red lines here, so this first red line is the recreational beach advisory for Ohio, and then 1.6 is the drinking water guideline for adults. And 0.3, which I don't have shown here, is for children. So we simply cannot predict toxins by biomass. And a lot of the research I have been doing is looking at, can we develop a toxin forecast? We've been making a lot of progress developing the toxin forecast, but we simply cannot rely on how green the lake is. So I'm going to talk about the dual role of phosphorus and nitrogen, and I'm going to introduce the concept of the limiting nutrient. And I'm going to use an analogy of building a car, because everyone knows, some of the key components in a car. So let's distill it down to, we have unlimited engine parts and all sorts of other things. But let's say if we only have one steering wheel and we have 9 tires, how many cars can we build? Well, the answer is 1, right? Because we only have one steering wheel and we have plenty enough tires. So in this case, the number of steering wheels limits car production. All right, so let's say we want to build more cars, so we go get 15 more tires, or we go get more tires. We have one steering wheel and a lot more tires. We can still only build one car because steering wheel limits production. Let's look at a different scenario. Now we have 3 steering wheels and 4 tires. Well, we can still only build one car, and we have 2 steering wheels left over. So now tires, the availability of tires limited the production, okay? So back to the initial scenario, 1 steering wheel, 9 tires, and we add in 1 steering wheel. Well, now we can build 2 cars, okay? We still have 1 tire left over, so in this scenario, number of steering wheels still limited production. So let's go get 3 more steering wheels and 7 more tires. Now we can build 4 cars. So in steering wheels was the main limiting nutrient or the main limiting factor for production, but increasing both the number of steering wheels and tires maximize production. And phosphorus and nitrogen work the same way in lakes. Phosphorus is usually the main limiting nutrient, but maximum algal production occurs with both high levels of phosphorus and nitrogen. And there are times when nitrogen is the main limiting nutrient itself. And we can test this experimentally with lake water. We do this through getting lake water from a lake, bringing it back to the lab, and we incubate it. Many different ways you can conduct these experiments. But let's just pretend these are bottles, and we have a control. Then we have a set where we add phosphorus, so we're elevating the amount of phosphorus, elevate the amount of nitrogen, and then elevate them phosphorus and nitrogen together. After incubation, if the ones that received phosphorus turn green, then we know that that initial condition was phosphorus limited. Um, Adding more nitrogen did not impact it because they didn't have enough phosphorus. This scenario here would indicate nitrogen limitation. And what we frequently see is that they need both phosphorus and nitrogen. So we would consider this dual nutrient limitation. There are times when we see um, adding phosphorus will have a little bit of an effect over the control, but really when we get phosphorus and nitrogen together, that's when we get the most algae growth. So let's look at nitrogen levels in Lake Erie. This is data that we have for 2018 and 19. We've been collecting data for many of years, but let's just look at these 2 years. The top two panels show Maumee Bay site, so near Maumee River. You can just ignore the different icons and site names here, but just look for the general trends. And then the bottom panel here is further out into the Western Basin. So every year we see a drop in nitrogen concentrations every year, very high levels in Maumee Bay in early summer, and they drop to near zero by August, September. The limiting nutrient for algae growth shifts. So phosphorus limits algae growth when nitrate levels are high in early summer. And then in the late summer and fall, both phosphorus and nitrogen limit algae growth when nitrate levels are much lower. And looking at the bottle experiments, so we can see that um, control phosphorus, but when we add phosphorus and nitrogen, the bottles turn green. So that was biomass. So let's look at microcystins, the one of the toxins they produce. So we see the same thing that adding nitrogen increases microcystins. These are just examples of a couple of experiments. Uh, Microcystin LR, one of the main toxins they produce, is 14% nitrogen by mass. So it takes microcystis a lot of nitrogen. Making microcystins is expensive in terms of nitrogen. So when we give the blooms more nitrogen, either nitrate, ammonia, or urea, we see that they increase the amount of microcystins. Adding phosphorus alone does not do anything for the microcystins. They really need microcystins, and we see this impact if we're doing it in bottles, small bottles, if we're doing it in medium-sized bottles, or if we're using our mesocosm facility. That microcystins really increase when we give it both phosphorus and nitrogen. So that was experimental data. So let's look at some observed data from the field. So on this graph, we have this is for 2016. Um, these black dots are nitrogen levels. And then the red triangles here are the ratio of microcystins to cyanobacteria biomass. And what that ratio indicates is it's letting us know how much microcystins are being produced per cell. Okay. As nitrogen decreases throughout the summer into the fall, we see that ratio of microcystins to cyanobacteria biomass decreases as well. So early bloom, early summer, the cells are producing a lot of microcystins. Late bloom into the fall, each cell is producing fewer microcystins. So that was 2016 data. If you want to see some more newer data, here's data from 2024, and these are sites in Maumee Bay and in the middle of the Western Basin. And we see that same pattern repeat itself. So early summer and July, lots of microcystins per cell, lots of microcystins per biomass, and then that decreases as nitrogen decreases as well. Um, I am also going to talk about briefly the role of light and water clarity in microsystems and how they interact with nitrogen. So this is an experiment uh, doing the incubation experiments where we have phosphorus and then three types of nitrogen. But in these experiments, we incubated the algae at different light levels. And what you can see is that under high light levels, the white bars here, that is when microcystin concentrations are the highest. So they need they need high levels of nitrogen and they need high levels of light. If you give them nitrogen but too little light, they don't have enough energy, not enough sunlight to produce microcystin. So they really need nitrogen and high light levels. In early summer, we have high nitrogen levels in the water. We have sunny days, longer days. The water tends to be clear, and these interact to allow the microcystis to have a lot of microcystins per cell. Late summer, available nitrogen drops dramatically. The days tend to be more cloudy. We get more storms, shorter days. The water tends to get more muddy, more turbid, and lower toxins per cell. Okay. And this is going to come back into play in a couple slides. So, we're talking about phosphorus and nitrogen. And one of the questions is, do we focus our efforts solely on phosphorus? So everyone agrees that 40% phosphorus reduction will minimize blooms. But what if we look at phosphorus and nitrogen reductions together? I'm going to present evidence from one experiment and model simulations. So these are experiments that Hans, Paerl, and I did with flake Curie water using one example here. Um, so on the y-axis, we're going to deal with how fast the algae is growing. Okay, so higher values here indicate growth rate, and then on the x-axis here is diluting phosphorus further down. So a 0% dilution would be that's what's in the lake to begin with. Okay, so when we decrease phosphorus, as expected, algae growth rate drops. Okay. So right now we're targeting a 40% phosphorus load reduction. Decreasing phosphorus concentrations will roughly half the rate that algae can grow in the lake. Okay, so that's where we want to be at. We can also see if we further reduce phosphorus by 60%, we will reduce growth even more. If we don't get to 40% and if we can only get to 20%, you can see we're still reducing algae growth. So any bit of phosphorus reduction will slow algae growth. Okay. In this example here, we elevated the amount of nitrate, amount of phosphorus and ammonia. Sorry, we elevated nitrate and ammonia in here. So there's ample nitrogen in these. But if we do dilutions where we co-dilute phosphorus, no, co-dilute nitrogen with phosphorus, which is the solid line here, we see that reducing nitrogen with phosphorus further slows algae growth rate. So if we will get a bigger bang for our phosphorus reduction buck if we reduce nitrogen with phosphorus. So that was the experimental evidence. Um, there's also environmental evidence from models where they ran different scenarios and specifically also looked at concentrations of microcystins in the lake. So at background levels, control here, nothing, there's no change. Okay, so if we do nothing, we won't expect any difference. The green dots here indicate cyanobacteria biomass, and then the red dots here indicate toxin levels. Uh, for now, we can just ignore the different shapes, just look at the overall colors. If we reduce phosphorus by 40%, the models agree we will drop cyanobacteria biomass in Lake Erie, but there would be a corresponding shift in more microcystins. If we reduce phosphorus and nitrogen together, we will drop biomass further, and we will also decrease microcystin concentrations. So why would targeting phosphorus only increase microcystin concentrations? It kind of comes back to that effect of light and nitrogen. So it follows if we have less phosphorus, we will get less phytoplankton biomass and less cyanobacteria biomass. That's the green dot here. But because there's less biomass, that results in more nitrogen being left in the water, which results in clear water. Okay, less phytoplankton in the water becomes clear. More nitrogen in clear water allows for higher percentage of the blooms to produce toxins, which means, we end up with more toxins per pound or more toxins per cell, however you want to look at it. And therefore, because we're producing more microcystins per cell, we end up with higher microcystin concentrations despite lower cyanobacteria biomass. So these two lines of evidence really point that we need to pay attention to nitrogen as well as phosphorus. So a hypothetical diagram, or not hypothetical, but a theoretical diagram um, we have for Lake Erie cyanobacteria blooms um, and toxin risk. So in the spring, when we get little rainfall marched through dry, we get a low phosphorus and nitrogen load. That results in a small bloom, and then ultimately you get a low toxin risk of toxin. In years and springs when we get a lot of rainfall, we get a lot of phosphorus and nitrogen load, we get a larger bloom, but then your risk factor for toxins depends on nitrogen. It depends on water clarity and sunlight. It depends on temperature, which I didn't talk about, and changes in temperature. The location of the blooms, if they're on the Ohio shore or the Michigan shore or getting pushed up into Canada, that depends on wind, waves, and currents. So all those factors interact depending, what toxins and what congeners are present, what genera, species, and strands of bloom is presented, and the location of the blooms and toxins. So a lot of the funding we've had has come from the U.S. uh, EPA through the GLRI project, the NOAA EcoHab project, and Sarah mentioned the uh, Great Lakes Center for Freshwaters and Human Health, and also the Ohio Harmful Algal Bloom Research Initiative. So with that, I'd like to thank for the invite, and I can turn it over to Hans now.
All right, Justin, thank you. And again, any questions for Justin, please write them in the Q&A and we will take care of those at the end of the presentation. Okay, Hans, you're up next. Perfect.
Almost perfect. There we go.
Whenever you're ready.
Okay. Well, thanks for inviting me, first of all, and thanks to Justin for really doing a great job in terms of spelling out the role of nitrogen in addition to phosphorus. I'm going to give kind of a big picture summary of what we know about nitrogen as well as phosphorus on a more global basis and what has changed over time in terms of how we're looking at nutrient limitation. And over time, I mean since the 50s and 60s, when things already got started on Erie in terms of bloom phenomena. So I think we all know this. This is just a kind of a overview slide here. Nutrient over-enrichment is one of the major problems that we're facing globally with water quality and ecological condition going downhill. And that's been acknowledged by the National Academy of Sciences as well as lots of other important organizations. And the scales and sources are also increasing. And I'm just showing you some, I'm going to go to my little laser here. Hang on just a second, please. Oops. Let's see here. Okay, there it is. So these are just some examples from places, actually most of them in the U.S., Lake Erie, obviously. Lake Okeechobee, over time in Florida, the largest lake in the southeast. The Gulf of Mexico, where the Mississippi River flows in, we've had increasing problems there. And these are the two estuaries I'll talk about a little later. the two major estuaries, Chesapeake Bay and the Alamo-Pamlico Sound. And then I'm going to talk a little bit about China, which has undergone really very rapid eutrophication due to excess nutrient inputs. And this is Lake Taihu. And by the way, the red indicates the amount of chlorophyll in the water as an indicator of algal growth. This is just a couple of slides showing you how fast nutrients have increased over time in Lodes, Mississippi Basin. We didn't have much of a problem there until we got into the use of chemical fertilizers more and also urbanization. And you can see that both nitrogen and phosphorus have increased. But this is an interesting part of the story. We went after phosphorus because phosphorus was identified as a limiting nutrient quite a long time ago. But we didn't do anything about nitrogen. And that has led to some problems in both the Mississippi Basin and the influent water into the Gulf of Mexico. Chesapeake Bay, same story basically. And also we can show that groundwater has increased as a major nutrient source. This just shows the increase in nitrogen in groundwater. And then here at home in North Carolina, we can see that both nutrients have increased as well over time in the Neuse River Basin. Again, we didn't do anything about nitrogen, and so you can see that nitrogen has increased dramatically relative to phosphorus. We had a phosphate detergent ban and more rules and regulations on phosphorus. If I have time, I'll get back to this story. And then in the Great Lakes, similar story. Things are more scattered here, and that has to do with wet years versus dry years, as Justin pointed out. But overall, the increase has occurred pretty steadily. It's starting to level off now a bit, but both nutrients have increased. So the nutrient eutrophication dynamics along the what I call the freshwater marine continuum, from up streams to rivers to lakes to estuaries and the coastal zone. The dogma has been that primary production and algal growth has been largely controlled by phosphorus availability in freshwater, nitrogen in estuarine and coastal systems, but accelerating human inputs of these nutrients has altered the nutrient balance and therefore the limitation in eutrophication dynamics as well. And I'm going to show you some good examples of that. So as a result, human impacted systems reveal a complex picture, particularly over the last 4 or 5 decades. And that's been a real challenge to the nutrient management. I'm going to start off with probably the most eutrophic example that I can think of and that I've worked at, and that is Lake Taihu in China, third largest lake. And it used to be a really nice lake in the 60s and 70s, oligotrophic, no major blooms. But then with the rapid urbanization in China, and you can see these cities here, Wuxi and Suzhou, both of them now are 7 million plus. In the 60s, they were less than 1 million. And then also agricultural development in the Taihu Basin has led to this issue where we now have blooms in the lake that last for 9 months or so. And they produce toxins and cause all the problems that Justin outlined. Here's just over time loading that has increased total nitrogen and total phosphorus. No surprises there, but interestingly enough, the nitrogen and phosphorus have increased by about 30 to 40% since the lake was bloom-free. And that number, 30 to 40%, is going to come back up. It's already up in Erie, where we're talking about 40% reduction, but also in North Carolina system. So the reduction data seems to indicate the increases that have occurred over time. And that's an important thing to remember. Now, what's the real problem in Taihu with regard to nutrients? Well, there's too much of everything, but it occurs at different times of the year. So you can see here, this is total nitrogen over total phosphorus over time. And these are 3 consecutive years. And you can see there's excess nitrogen here in the spring, as Justin has pointed out, due to agricultural inputs and a lot of inflow by rainfall. But in the summertime, the TN to TP ratio falls below this magic red line, the Redfield ratio, which means balanced growth, is sort of what you would like in terms of the relationship between nutrients and algal growth. And this repeats itself in the 3 years that we worked there on that. So we hypothesized from that that the lake is maybe phosphorus limited in the spring because of that excess nitrogen, but then in the summer, you see things fall below the Redfield line, so maybe that's a nitrogen limited period. And we tested that with bioassays. I'm going to talk quite a bit about bioassays in this talk. But bioassays are basically, as Justin has pointed out, you collect the lake water, put it in containers, all sorts of containers, and then incubate it under natural light and temperature conditions. And what we see in Taihu is that in the spring, if you look at these are the nutrient limitations that we see. So here's N, here's phosphorus, and here's N and P together. You see that phosphorus tends to be the limiting nutrient here in the spring. With all that, phosphorus tends to be the limiting nutrient in spring. So if you add it, you increase the biomass. But in the summer, the whole thing reverses to nitrogen limitation. Here's nitrogen, and you can see that it comes up. Phosphorus, not so much, later in the summer. And then the next year, we see a similar pattern with phosphorus addition stimulating, but then in the summer, nitrogen addition stimulate. But the thing I really want to point out is that if you add N and P together, you get more than N alone and P alone. This is kind of starting to sound like a broken record, but it really matches well with some of Justin's conclusions as well. And, for politicians who don't like to look at data, I have a special slide here, which shows us 50 milliliters of bioassay water that is filtered onto a glass fiber filter after 24 hours of incubation in Taihu. Here's the control, no nutrients. Here's nitrate addition. You can see the stimulation, phosphorus stimulation as well, but not as much as N and P together. And this is a very effective way to show slides without showing results without data, by the way. Managers love these kinds of slides. So the bottom line is that, and I'm actually showing you some results from bioassays in China, where I'm comfortably sitting over here after 24 hours of incubations in the lake. And you can see the controls here, the triplicate controls are the clearest. Nitrogen only, starting to get green. Phosphorus only, still clear. But N and P together, this is ammonium with phosphorus, and this is nitrate with phosphorus, stimulate. So in this lake, both nutrients are really important, and nitrogen is very important because it's the key nutrient that controls the blooms during the summertime. So the question then arises, well, is Taihu a good looking glass for eutrophic or eutrophying systems globally? And I'm going to just show you a few examples to reiterate this N and P together issue. This is just a repeat slide of Erie, but I picked out some interesting data from Sandusky Bay, which shows you that relative to the control, again, these are all bioassays incubated in the, here right off the Stone Lab, by the way. Nitrate addition stimulate relative to control. Ammonium, urea, all these are nitrogen sources. Phosphorus, not so much. And N and P together give you the most. So, we're looking beyond phosphorus only limitation now. And that's sort of changed the paradigm relative to the 50s when nobody was talking about nitrogen and we were concerned largely about phosphorus and carbon. This is data from experimental lakes where the whole lake fertilization took place. The Canadian experimental lakes areas included lakes in Quebec, Northwest Territory, and Sweden. And what you can see is that relative to controls, so the controls here would be the line, you can see in terms of chlorophyll that nitrogen stimulates on its own in many of these lakes. Phosphorus, surprisingly, not so much, but it does in some lakes. But N and P together give you the most. So we published a paper on this in ES&T with a little cartoon to indicate that of these lakes, 9 of them showed phosphorus limitation, 4 of them nitrogen alone, but 12 of the lakes were N and P limited. So co-limitation is dominant in these systems, particularly in the summertime when we get these blooms and we see that both N and P are really important. And globally, you know, the cyano-HABs are encroaching along the freshwater to marine continuum due to increased nutrient loading. Most are N and P co-limited, with just some exclusively nitrogen limited as well. And this is all based on experimental work by our colleagues and published in the UNESCO summary document that I'm more than happy to circulate around. If we go to a riverine system, this is the Chowan River in North Carolina. It borders Virginia here to the north, and it has massive blooms on it in the summertime. Again, we did these bioassay types of experiments where we collected water from the Chowan, brought it over to our lab here in Morehead City, and you can see that in after 72 hours incubation, again, we're using chlorophyll here as an indicator. Nitrate stimulates ammonium, urea, phosphorus, and I can't see the other thing because it's hidden. Oh, here we go. N and P together give you the most. And the same story here several years later. This is actually a student project that shows very similar results, N and P co-limitation. Oops, why am I not? Okay. So let's go to estuarine and coastal systems. And what do the data tell us there? This is a relationship between inorganic nitrogen loading and primary production. It's old. It's from an old paper by Scott Nixon, but it's a great paper. And it shows a very direct relationship between inorganic nitrogen input and primary production. So, you know, nitrogen increasingly important in those downstream systems in estuaries. And I want to point out that, you know, we really need to look at this nutrient limitation not only in the freshwater systems, because that water flows downstream into our estuaries and coastal systems, so there's an impact there as well. If we look at the largest sort of brackish water system in the world, the Baltic Sea, this is data from cruises that we did, and Pia Moisander, one of my students, published a nice paper on this. This is primary production. Nitrogen stimulates, not phosphorus. We added iron to see if it made a difference, but it didn't. And N and P together give you the most, and also the same results with chlorophyll. Chesapeake Bay. This is data from Tom Fisher and his colleagues that is really a very comprehensive look at bioassays over time and along the axis of Chesapeake Bay. So this is the distance from the ocean here. This 0 would be here, and the Susquehanna River input up here in the north would be the farthest away. But you can see that in the wintertime, light limits production because it's dark and short light period. But phosphorus starts to become the limiting nutrient. This is a very similar story to Lake Erie. And then nitrogen in the summertime again, and N and P in the fall, and then light limitation in the wintertime. So light does interact with nutrients as well, as Justin has pointed out, both in terms of biomass production and toxicity. North Carolina's Neuse River estuary, very similar story. Nitrate, ammonium, and organic nitrogen as urea stimulated, and then N and P together give you the most relative to P and N alone. Now, I want to show you a couple of slides that make these kinds of data really relevant to management. This is the Himmerfjorden in Sweden, which is a freshwater fjord that flows into the Baltic Sea. Here it's kind of brackish, but this is all freshwater in here. And it's upstream. Upstream is Stockholm, the city of Stockholm. And one nice thing about this, if you're interested in looking at nutrient dynamics, is that there's one big source of nutrients there, and that's the sewage treatment plant up in the upper part of Himmerfjorden. And this has suffered from eutrophication since the 60s or so. And my colleagues, Ulf Larsen and Ragnar Elmgren, did some really nice work here showing relationship between those nutrients and the bloom problem. So don't worry too much about the Swedish, but this is basically loading into the Himmerfjorden. So the Swedes were aware of the phosphorus problem well into the 60s. So they controlled phosphorus pretty strongly by both treating phosphorus at the wastewater treatment plant, but also a detergent ban at the same time. So you can see phosphorus is quite low, both total and dissolved in organic phosphorus. But like everybody else, they didn't really worry about nitrogen because it wasn't really on anyone's radar screen at the time. Then the blooms developed in the 80s and 90s, and even despite the phosphorus reductions, the blooms didn't go away. So they decided, let's reduce nitrogen and see if that's going to have a beneficial effect. So they instigated or initiated denitrification as a way of getting rid of nitrogen at the wastewater treatment plant. And there are two periods here where they did that experiment, and then, like good scientists, they said, well, let's go back and let nitrogen go back into the system. So what happened? So here we got the nutrient data. Here you can see the DIN levels slowing down or being reduced due to denitrification. And then here's chlorophyll, surface chlorophyll, and you can see there's a nice drop there in chlorophyll. And then when they allowed nitrogen to go back in the system, chlorophyll increased. So from that data, they developed a nitrogen loading bloom threshold. And I think this is a great example of using basic data, the kind of stuff that Justin and I do, and putting it into management strategy. So here you can see that the loading of total nitrogen in tons, if the impact on chlorophyll. So as long as you stay below 400 tons per year of nitrogen, you can control chlorophyll and you can control blooms. But if you go above that, you're pretty much into the bloom period, even if you reduce phosphorus alone. And that's because there's a lot of phosphorus there already in this system. So again, here it's just a good example of managing nitrogen to improve water quality conditions. So one question that comes up, and it's come up in Lake Erie, is, why doesn't nitrogen fixation support the nitrogen requirements in this continuum? And of course, nitrogen fixation is the process by which, among other organisms, cyanobacteria can take nitrogen from the air and provide fixed nitrogen to support its growth and also eutrophication in the system. The answer is it's not because there's a shortage of nitrogen fixing taxa. This is a genetic tree of the nitrogen fixing gene, the NIF gene, and you can see there's lots of cyanobacteria that have the capability for fixing nitrogen. So that's not the reason why there isn't more nitrogen fixation going on. But if we look at just a little bit of biochemistry here, hopefully not above anyone's head, what controls nitrogen fixation from a biochemical perspective? Here's the enzyme that controls nitrogen fixation, nitrogenase. It's a 2-unit enzyme, and it's of course supported by energy to fix nitrogen and put it into ammonium, which then would go into growth and algal production. And the phosphorus, the popular phosphorus hypothesis is that, well, if you reduce phosphorus, you'll reduce nitrogen fixation activity. But there are other factors that control nitrogen fixation, and Justin already mentioned light as an important factor. Photosynthesis, if there's not enough light going on, you need light to provide the energy to make this process go. So light is really important, and also organic matter in the system is important because there are bacteria that can fix nitrogen too. Iron might be important because it's part of the enzyme complex, and oxygen is really important because this enzyme is inhibited by high oxygen levels. So when you get a big bloom, like we see in Erie in the surface waters, the dissolved oxygen level can be supersaturated. It's often like 200% saturation. So that can bring into the game oxygen inhibition of this enzyme as well. So it isn't just phosphorus that provides the necessity for fixing nitrogen. Energy is really important, and dissolved oxygen may be important as well. So we looked at eutrophic systems. These are small lakes, and you'll see some are very familiar to most people. And we looked at the annual nitrogen fixation rates that are here. And then we also looked at the denitrification rates, which is the loss rate for nitrogen out of the system. So this is the input to the system. This is the loss. And when you look at the net flux of nitrogen, it's always negative. And what that means is that denitrification exceeds nitrogen fixation as in terms of the balance of nitrogen. So the take-home message here is that N fixation does not meet the ecosystem N demands, including in Lake Erie. And also what that means is that more nitrogen inputs will accelerate eutrophication to overcome this negative flux that occurs in the system. So really the most important part of this is we got to get serious about controlling nitrogen in addition to phosphorus. One other thing is that phosphorus retention time in these water bodies is very high. And what that means is that phosphorus that gets in stays there. It doesn't go anywhere because there's no atmospheric loss mechanism like there is for nitrogen. So the retention is very high in most lakes. And I want you to keep that in mind because this conceptual diagram kind of shows you the relationship then between the balance of N fixation and denitrification. So here are the nutrients coming in. Orange is for phosphorus. The black is for nitrogen. There's also atmospheric inputs, by the way. They provide the nutrients to support primary production. That primary production then provides the energy source for nutrient recycling in the system, including denitrification, and it also supports nitrogen fixation in the surface blooms. But if you look at the thickness of these arrows, nitrogen fixation is less than denitrification in the system. So the system is always kind of nitrogen hungry and then becomes nitrogen limited. The only way phosphorus can leave the system is by advective losses, and those are pretty small in terms of the relationship to loading. And as a result, we get what's called this legacy load that that hinders often using phosphorus reductions alone because the phosphorus is trapped in the system and it's just cycling between the sediments in the water column. Whereas nitrogen can be lost to the atmosphere as well. So as a result, just to sum up things, the freshwater to estuarine and coastal continuum appears to be both N and P co-limited most of the time. And that's strongly impacted by human activity, particularly if we consider historic loading, for example, of phosphorus that was loaded into Lake Erie a long, long time ago and is now the legacy of phosphorus in the lake. In most ecosystems, nitrogen fixation does not meet ecosystem demands, perpetuating nitrogen limitation, okay? And so more nitrogen inputs lead to more eutrophication. So the recommendation overall for these systems is hold the line on P reductions for sure, but parallel N reductions are going to be needed to control eutrophication along the continuum. And from a climatic perspective, increases in major storms and runoff and increased wet-dry cycles play a key role in eutrophication, as we've shown for Erie with the spring inputs, for example. So the last thing is continuous monitoring is critical for gauging long-term success and the needs to adjust these loadings over space and time. Do I have a little bit more time?
Actually, yes, you do.
Well, this is sort of my concluding slide, but we'll go back to that. What I wanted to show you is in North Carolina, historically, what has happened in terms of phosphorus reductions and nitrogen reductions. So, nutrient management along the freshwater to marine continuum, and we're talking about the Neuse River going here from a freshwater systems into an estuarine system. Nutrient management along that continuum from the 1980s into the next century is shown here. So here's TN, okay, and TP loading or concentrations due to loading. And you can see that TP was very effectively reduced in the 80s, in late 80s and 90s. And that's because we had a detergent ban and improved treatment at wastewater treatment plants. So that's a success story. Okay, and it was a success story for the head of the estuary, which was largely phosphorus limited. You can see here's the data for the head of the estuary. You can see that the chlorophyll levels dropped really nicely in the upper part of the system, but mid-estuary and lower estuaries, the chlorophyll levels actually increased. And we think that's because we didn't do much about nitrogen. So what has happened? What's the mechanism that has allowed estuarine systems to increase in production, even though we reduce phosphorus upstream? So here's kind of a sideways look at the Neuse estuary. Here's the 70s and 80s, and here's the phosphate detergent ban, which led to the big decrease in phosphorus. And then we go on beyond that with some interesting storm activity and stuff that I won't talk about now. But this was sort of the pre P-band kind of data with phosphorus and nitrogen being high. And as a result, the chlorophyll maximum was up in the riverine part of the system. But then when we reduce phosphorus, we also reduce the filter for, we also reduce the growth potential of the phytoplankton in the upper part of the system, which were largely phosphorus limited. So more nitrogen got through the filter into the estuary. And as a result, the estuarine system showed more eutrophication even after a phosphorus reduction strategy. So as a result, we've had to reduce both N and P together based on dilution bioassays. The recommendation now is a 30% reduction in N, along with the earlier reductions that occurred in the system in the 80s. So again, the dual nutrient issue is really important, whether you're in lakes, rivers, or estuarine environments. And I think I'll stop there so we can have some questions from the audience. And I just wanted to acknowledge that, we're part of this Great Lakes Center as well. But also there's been a lot of additional funding of this work by NSF, North Carolina Sea Grant, and the collaboratory that we have in North Carolina as well. So I'll stop there. And thank you very much for letting me join you.
Any questions? Actually, I do have one question from for Justin. I believe it'd be for Justin. You mentioned in your presentation about testing for microcystin. I guess I was wondering if is it pretty easy to test for microcystin, and do you think down the road is this might be some kind of a general public item that could be maybe available to people who maybe have a pond or live near the lake to test for microcystin?
Uh, maybe. Um, so the gold standard for microcystins, well, there's two methods. They're expensive, require a lot of equipment, a lot of training. The the ELISA test, which Ohio EPA requires all drinking water plants to use, and that's what our basically all our guidelines, Ohio, US, and WHO are based on ELISA data. Um, the minimum takes about 8 hours from
Mm.
sample to data, and a lot of times it's longer than that. Um, However, there are several companies and researchers looking into can we decrease that time? And they're coming up with all sorts of gadgets and gizmos that are supposed to be portable, cheap, whatever other benefits. They all struggle from the same concept that for microcystins, most of the microcystins occur inside a cyanobacteria cell. But in
Mm.
order to measure the microcystins, we have to break the cells open
Mm.
to release the microcystins. The second part of that equation, once the microsystems are in the water outside of the cell, most of the methods are showing some success that they can be used. However, it's breaking that cell open is the key part. Because if you just take their analytical method, buy it as is, you're going to miss 90 to 95% of the microsystems because it's inside the cell and the reagents or the chemicals, whatever they're doing, can't penetrate the cell.
Mm.
So that breaking that cell open still takes, for example, in Ohio and many places, we freeze the sample, thaw it, freeze thaw, freeze thaw, freeze thaw to break it open, and that takes several hours. Um, so there are some companies that are trying to reduce the analytical time. It's still the thawing process still takes time, and there are some other methods that are being worked on to increase the lysing procedure, but um, we're not there yet. And those analytical methods are still somewhat suspect.
Okay.
They
Fair.
work sometimes and they don't other times. So
Yeah,
maybe.
that makes sense. It would be nice, but yeah, absolutely. All right.
Can
Well,
I follow up on on Justin's comments?
absolutely.
Um, he mentioned cells breaking open, and that gave me a thought about controlling blooms. We've talked about nutrient reductions as, sort of the overarching strategy for reducing blooms and mitigating them. But there are other strategies that have been used, including putting in chemicals that will kill the algae, including copper sulfate, for example, and other chemicals that are now more in use. Hydrogen peroxide is another one in small lakes. But what I want to point out is that when we do treat the water with these chemicals, it'll lyse the cells that are harboring the toxins. And so what that can do is release the toxins into the soluble state, which makes them much more difficult to get out of the water than if we filtered the algae out, for example, in a wastewater treatment plant. So chemical treatments, while they give you quick results sometimes, can actually lead to complications, both from the ecological and the human health perspective. And this is one reason why no matter what people want to do to kill the algae or get rid of them, got to accompany it with nutrient reduction. So even when you apply these chemicals, often you have to reapply them, certainly more than once a year. And the following year, because the algae will have spores that'll sink down to the sediment and start new blooms in the following year. Um, so, it's not as easy as it sounds to get rid of the algal bloom problem, particularly over the long term. And the fact that the cells are killed is great, if you want to show a clear lake a couple of weeks after the treatment, but then you got the long-term issues like solubility of the toxins, hard to remove, and repeat phenomena. And the only way to really deal with repeat phenomena is to maintain nutrient input reductions of both nitrogen and phosphorus. I just wanted to emphasize that. Thank you.
Okay. No, thank you. Very, very insightful. Very good. Well, it doesn't look like there's many more questions, so I think your speakers are getting off easy today. And but if you any questions that come to mind, please feel free to reach out to me at torlina.1@osu.edu, and I will certainly make sure they get to our speakers. So we
And
are
if
gonna off.
anyone,
Oh, go
sorry,
ahead.
if it, yeah, if anyone has specific questions for us, uh, please feel free to email me. I think my email, well, yeah, it's my, I'm easy to find.
No,
It's Hans,
absolutely.
Hans_Paerl, Paerl at unc.edu.
Perfect, perfect. And like I said, you guys reach out to your speakers or reach out to me, and I'll make sure any message gets to them. So appreciate you, all three speakers. Thank you very much. In fact, thank you for joining us. Again, please join us for a couple of events coming up. First on Monday for a CLM webinar. in the registration is listed. And February 25th will be our next Water Quality Wednesday webinar. And feel free to register for that. So if you have any questions, feel free to reach out to me or anyone on the water quality team. And I want to thank everybody for joining us today. We'll see you next time.